All right, what I want to do here is look at energy in an electric field. I think to do this we'll use the capacitor, and that's because, as you saw, the electric field near a point charge changes. It is not uniform, and therefore the calculations get more complicated. So we've actually got our uniform electric field in there, and I think if we go with the same dimensions we had on the last one, it makes the calculations easier, which was this whole setup is 5 millimeters from plate to plate. We've got 1000 volts. So our electric field is 200,000 volts per meter. And what we did there was we had this little electron, and we said if the electron was there, it would experience a force towards the positive plate, right? And we said if it does actually fall towards the positive plate, I call it fall because it's just acting on like a field. That's what happens when you fall here, but it's a gravitational field. Then that's negative energy because it goes with the force, negative change in potential energy. Now, because there's no such thing as really negative energy, is there? There's just a positive change or a negative change. Does it increase energy or decrease? Now, we have this equation, F equals EQ. That's electric field times that. But we've also got this other equation, which is that work equals force times distance. So surely that just means we can go work equals EQD. And we can, and we'll find that it's one of your formulas, all right? That means that if this little charge was in the middle, then it's going to move 2.5 millimeters. Now, we worked out the force in the last video, but we can do it again. The work for this little charge to move from here to here is just going to be equal to EQD. Now, E is 200,000. Q is 1.6 times 10 to the minus 19. And D is 2.5 times 10 to the minus 3. That's just your changing millimeters into meters. You divide by 1,000, which is the same as multiplying by 10 to the minus 3, right? So we've got 200,000 times 1.6 exponent minus 19 times 2.5 exponent minus 3. And here we got it, 8 times 10 to the minus 17. And that's joules, right? That's done in joules because it's energy. So that's our calculation of work, but it's negative because, like I said, if you go with the field, the change in potential energy is negative. All right. So, well done us. We've calculated that. What I wanted to do now, though, was just have a little look at a few of the other bits of maths that might sort of crop up here. And the one I'm thinking of is V equals E D. Now, let's just see some relationships. Voltage is energy, so this is energy, not the electric field, divided by charge. So it's joules per coulomb, right? Now we just said that, so we could say that energy or work equals VQ, right? But we just said that work is equal to EQD. So we can say, so if we say that work is equal to EQD, then, and that's this one, then V must be equal to ED, which is what we used initially to calculate the value for the electric field. So there we go, energy in an electric field.